So in this case, we're identifying the particular solution in the graph that goes through the point. So the figure to the right shows the slope field for the differential equation right here, and we want to sketch the graph of a particular solution that contains 0, 2. So 0, 2, that's right here, and that's point A. So all we're doing here, you can think about this as like a current, like an ocean. Where does it go? You just follow the path here. So to the right, you see we're just following this path. We're following this path. You see it kind of flattens out right here. Draw an arrow sign. And then from the left, you just follow the path, follow the path, follow the path, follow the path. It looks like it flattens out roughly right here. That's point A. Point B is -1, -2. So if you follow the path, right, it looks like from the left, it's going approaching roughly the same thing right there. And then on the right, you just follow the path, follow the path, follow the path. You see where approaches flat lines there as well. And that is point B. That's all you do with these problems. You just follow the path, plot the point, follow the path. So this question here, the slope field for a certain differential equation is shown to the right. Which of the following could be a solution to the differential equation with the initial condition, well, to the point 0, 0. So 0, 0 would be right here. If you follow the path to the right, it would just go up like that. And then from the left, you see it go kind of up like that. So again, this is not what we did before, where it's like dy dx is equal to these, where you just plug in coordinates and see what works and what doesn't. This is the actual graph itself. So for these, you can honestly just graph using your calculator here. So keep in mind it looks like this, right? And well, I'll tell you the right answer. The answer is D. If you plugged in x squared 2 plus x, you adjusted the window so it's -3 to 3. For the x min is -3, x max is 3, and the y min -3 to 3 as well. You graph it, you see how it's the same thing here. I'm not going to graph the other ones, but if you graph the other equations, you would get something completely different. So this here is just your answer. D. This next question here, 3. Consider the differential equation dy dx equals x plus 1 over y. Describe all points in the xy plane for which dy dx is equal to 1. It's pretty straightforward. All you do is set dy dx equal to -1. So x plus 1 over y is equal to -1. You multiply y on both sides, so x plus 1 is equal to -y. And then you can just multiply both sides by -1. You get y is equal to -x minus 1. So all the points that fall on this line here, you can just write that right there. And if you see all the, so on the slope field, right, you see, and this where I circled, right, you see all those hash marks are -1, -1, -1, -1, -1. This is the line that describes that, what we did right there. So, question 4, explain why the following could not be a slope field for the differential equation dy dt equals -0.3 y. So, if you plugged in y is, let's say, when y is, let's say, 3, let's say y is equal to 3, then dy dt is equal to -0.3 times 3, which is a -0.9. So what this is saying, right? When y is equal to 3, every hash mark around what I circled should be a -0.9. But you can see at 3, right, at 0, 3, it's 0. But then as x increases, the slope's going down, but it shouldn't matter because it should only be influenced by the y. But you can see every slope field hash mark in here that I circled is different, even though the equation is saying it should be negative 0.9. Therefore, therefore, this could not be a slope field for this given equation. And you can write that out however you'd like. You could just say, like, when y is equal to 3, all the slopes are not negative 0.9. Again, there's different ways you can word this, different points you could have picked. If you're unsure when you're doing the practice, please let your teacher know just to check it over. You can start the practice.